Good morning and welcome. Hope you had a good Easter. So, we are about to finish up the course, and the program for today is the two-dimensional convection-diffusion equation, and tomorrow we'll also look at the two-dimensional incompressible Navier-Stokes equations. To give you an idea of that, I just start the program Solar that Radar supplied as on demo 11. So those who were not present, you can also see the demonstration. There's also a video of that. And what we are solving here is the incompressible Navier-Stokes equations. But the basic ingredient in that is the solution of the momentum equations, which are of the kind of convection-diffusion. And that is what we focus on today, before looking into the algorithm behind this program Solar. So while this is running, we start with the title 2D Convection-Diffusion. Equation. Okay, there it has finished. So that is actually exercise 12. So you'll get velocity profiles for the v direction, for the u direction. You get streamlines, and the problem. Sorry, I forgot to tell those who were not there. The problem is that we have a square cavity. We can enlarge it to make it clearer. So we have a square cavity. And these boundaries, these three boundaries, are fixed, but the top boundary is moving with a constant velocity to the right. So it's a lid that is then driving the flow because of the no-slip boundary condition. The fluid here will be moved in that direction, and we get a vortex. So you see here the indication of that in the streamlines. And another result is the pressure, which is not so exciting, except for this singular point where the velocity is here. It's non-dimensional 1, and here it is 0. So but nonetheless, that's no problem. But we have a pressure spike here, large pressure. And else we have the streamlines. So that is something that you are going to play around with, and also to do some other visualization with that. For example, the vorticity, and you have the classical paper by Gia et al., which Radar supplied, where you can compare your results with those from literature. So that is an example of, as I said, solution of the convection-diffusion equation inside solving the Navier-Stokes equations, because the momentum equations are, in fact, convection-diffusion equations. So, therefore we start with this, and as usual, we start with a physical and mathematical classification. So if both convection and diffusion of a physical property in 2 dimensions are considered, we obtain the 2D convection-diffusion equation. So far we have only considered these effects separately. Remember when we considered, well, let's first just think in 1 dimension. In 1 dimension we discussed first the heat equation, also the diffusion equation, where we have only a diffusive effect. So where discontinuities are smoothed, and if we have waves, the amplitude is damped. And then we looked at the 1D linear advection equation, where we only had advection present, and there is only a velocity profile or whatever profile of temperature or concentration is just transported without change. And in this equation we have both present, both diffusion and advection. But advection is here called convection, that is a convention. And the equation looks like this. We have a physical property. We take example later on, which might be temperature, concentration, or even velocity itself. So you would now think of temperature as a starter. And then we have a velocity vector that is doing the transport, which I denote the x component by c1. I'll give that detail in a minute, times du dx, plus the y component denoted by c2 of the advection velocity, times du dy. So if this were 0, then we would have the 2D linear advection equation. But it is not 0, because on the right-hand side we have a diffusion coefficient, alpha, and we have second derivative of u with respect to x, and second derivatives of u with respect to y. So that is our 2D convection diffusion equation. It's easy to imagine what this is in 1D, just we take then away the y derivatives. It would be in 2D, we would just add the ct, c3, du dz, and here a second derivative of u with respect to z. But we concentrate here on 2D to make things a little easier. And in here, the advection velocity, c, has the components c1 and c2 that are appearing here. So that is a given advection velocity. And the alpha is assumed to be greater or equal to 0, and that is a constant. We assume that it is constant, and for the moment we shall also later on consider the c also as constant. That here the alpha is then a constant diffusion coefficient. So that is the equation. Now, to give it physical contents, we look at a few examples. The first example is the simplified (2D) energy equation for incompressible flow. And that we can write in the following way. Then the advected and diffused quantity u is temperature. So we have the time derivative of temperature, and then the velocity is actually the velocity that we have in our flow problem, and that might not be constant, but it is given. So u is the velocity component in x direction, and v the velocity component in y direction. And on the right hand side we have, in that case, the thermal diffusivity times the second derivative of the temperature with respect to x, and the second derivative of temperature with respect to y. So, and in here we have T temperature, V, that is with the components u and v appearing here, that is the given velocity vector, and u and v are the components in x and y direction. And they might depend on x, y, and t actually. That is possible, and that is in fact so in practical applications. So that is then an example when the convection velocity that we have here, the c, is not constant. And the alpha that we had already when we discussed the diffusion equation, in fact when we discussed the heat equation, that is the thermal conductivity K divided by the density times the specific heat at constant pressure. So that is the thermal diffusivity. Okay, so then we have these examples. This form that we have here is the so-called non-conservative form, because we have here a derivative. We cannot write this as a total x derivative because we have the u in front, and here this is we cannot write it as a total y derivative because we have the v in front, but we can write it in conservative form using the continuity equation. So we can just note that this form that we have here is a non-conservative form. For the discretization, it is usually advantageous to use the conservative form to have the conservation properties also then when we do the discretization. Mathematically, they are completely equivalent. So, but we note here that due to the continuity equation, which is, as we know, the divergence of the velocity vector is 0, we have equivalently in 2 dimensions that du dx plus dv dy is 0. So that is the continuity equation in Cartesian coordinates, and if we use that here, then we can write the u inside the derivative. So then we have ddx of ut and ddy of vt using this. So then equation 2 can also be expressed in conservative form. And that is tan derivative, that is the same. And now we write that what I just indicated. We have now the u inside the derivative. And likewise with v, we have vt respect to y. On the right hand side, that is already that's the same. Second x and second y derivatives. So that is then the form that we have here is then the conservative form. So that is an example for heat transfer, which is frequently used. Just a remark on why this is the simplified form. We have made here 2 assumptions. One is that we assume that the specific heat at constant pressure is equal to the specific heat at constant volume. Cp is equal to Cv. Because Cv would appear naturally here. And the other is when we have the 2D energy equation for incompressible flow, we have also a term here coming from the heat generated by the viscous effects. And that is the diffusion. Let's see, that is the dissipation function. And this dissipation function is neglected. That can often be done, but if you want to read about that, you can do that in the textbook. There the full equation is written. So, let's see, just mark the equation. Energy equation, full energy equation. We can look in the textbook, which is the Pletcher, Tenhill, Anderson. That is the edition 2013. You will find also that in the second edition and in the first edition, but I refer to the third edition here. That is 253, 254. You see also that derivation from the energy equation for compressible flow. Okay, so then we have this example. And in this example, we have in fact assumed that our advection velocity is not constant. The second example is very similar. That is the 2D species continuity equation. What you have when you have multiple species in air or in liquids or in other gases, whatever you like in any fluid. For example, in combustion, you have CO, CO2, and different components that you have when you do combustion. Then we can write for each of these species species continuity equation. And this looks like the following. I write it here in terms of the mass fraction y. I'll explain that in a minute. That's a way of characterizing the concentration of this species. Imagine we have here the concentration or the mass fraction of CO2 in a mixture. Then we have again, as for the energy equation, here the velocity, which might again be, usually is not constant, but is a function of time and space. So we have the first the x derivative, and then we have the y derivative, the v, velocity component in the y direction. On the right-hand side, we have the diffusivity, which is this curly d. We assume that it is constant. And then we have the second derivative of the mass fraction with respect to x, and the second derivative of the mass fraction with respect to y. But if we have reactions, we usually have also a source term, denoted by s of y. So that is then, and if we have, for example, 5 species, we would have 5 of those species continuity equation for each of them. So the y is the mass fraction of the species that is considered. For example, if we look at this example of the CO2, then it would be the mass of the CO2 in the mixture divided by the mass of the mixture. And in the mixture we might have carbon oxide singular atoms, or we might have molecules CO, so we might have O2. So then, and that would be then this ratio, that is called the mass fraction. That would be the mass fraction, this example of CO2. Okay. And V is as before the velocity vector, like in the simplified energy equation. It's like velocity. And the D, the curly D, is the diffusivity, which plays the same role as the thermal diffusivity here. It's an indication of how much diffusion is happening. And the S, that is the source term, due to chemical reactions. If we don't have it, then it will be 0. But in combustion, this plays an important role. And in this derivation, it is assumed that the density of the mixture is constant. So, rho, density of the mixture, rho is assumed constant. It would not be much different if we would take also a variable density into account, but to have it in the form of the convection-diffusion equation, this is easiest to have the density constant. So, if we don't have reactions, the source term is 0, and then we have immediately the convection-diffusion equation. And if we have the source term, this equation is often called the convection-diffusion reaction equation. But we shall here not consider this, I just take it as an example. So equation 4 is an example of a convection, fusion, reaction. When we have all three processes present. The convection is due to transport, just translation, diffusion, where we have a smoothing effect, and reaction, where species might be generated or dissipated. So that completes the example of the 2D species continuity equation. And now we have also another example, actually from the Navier-Stokes equations themselves, namely the 2D linearized momentum equations. Or if we consider it as a vector, that would be for the vector, and that would be for incompressible flow. And that we can express in the following way. Now I express it directly for the vector, and I denote the perturbation by prime. I'll explain that in a minute. So we have the time derivative of the velocity perturbation plus, and now we have a uniform flow with x component u0. Then we have here the dv prime dx. And we have a velocity, uniform velocity with a y component v0 times the velocity perturbation derivative in y direction. On the right hand side we have nu, the kinematic viscosity times the second derivative of the velocity perturbation with respect to x and the second derivative of the velocity perturbation with respect to y. So, and now the explanation. The velocity vector is decomposed into a uniform component, which is constant, and a perturbation. So the uniform component is denoted by v0 and the perturbation by v prime. So that is the velocity vector. And now the v0 and the v prime are then uniform flow and perturbation respectively. All right. So the v0 that has then the components u0, v0 that are appearing then as the advection velocity in the equation. So that is assumed to be constant. That is the uniform flow velocity. As an example, you could imagine we have uniform flow. If we have, for example, an airfoil in a wind tunnel, that is then uniform flow is approaching. So then the u0 would be constant, the v0 would be 0. Then we have small perturbations on that. The perturbations are then denoted by the v prime. And they have then the components u prime and v prime. So that is then velocity perturbation vector. And that is interesting to study effects of small perturbations on the flow. There's a stability theory, flow stability theory, where that is done, and then we can actually predict approximately where there is the onset of turbulence. But that is not what we want to do here. We take it just as an example of a convection-diffusion equation. But important in this consideration when we do the linearization is that we assume that the perturbation modulus is much, much smaller than the modulus of the uniform flow. So that is the assumption. That means also that each component, u prime and v prime, is much, much smaller than the uniform flow velocity modulus. And the u that is appearing, that is, as you know from fluid mechanics, the ratio of the dynamic viscosity and the density, that is the kinematic viscosity. And that is assumed to be constant. When we do the derivation from the two-dimensional momentum equation, from the Navier-Stokes equation, then we use this fact here that the perturbations are much smaller than the uniform flow to neglect products of u prime and, for example, du prime dx. So these products where we have two small quantities multiplying with each other, maybe a derivative over that, those are neglected. That is called linearization. If we do that, then we derive this equation. So it is not the full equation, but these nonlinear terms are simply neglected. But it is an example of a convection-diffusion equation. In fact, here the u0 and the v0 are constant, so we have a constant advection velocity. We have here then the advection, and here we have the diffusion. And the diffusion coefficient is the kinematic viscosity. So if that is large, if we have honey, for example, then the viscous effects are much larger than convective effects. And the other way around, if we have air, say for an aircraft, then this part is usually, the diffusion is much smaller than the convective fluxes. And that ratio is given by the Peclet number. So let's just look at that, because that is interesting to characterize the importance of convection and diffusion. So the Peclet number following, that is 6. Peclet number is, and we define it, if we go back to the original form 1, the advection velocity was denoted by C. Here it would be the uniform flow vector V0 with the components U0 and V0. This is from the general equation 1. Then we have here a length scale that we need in our problem, divided by the diffusion coefficient. So that is the ratio of the convective and the diffusive flux. So that is equal to C U. U is now our advected and diffused quantity. In this example, it is actually velocity perturbation divided by alpha U over L. And this is the ratio then of convective flux divided by diffusive flux. That is then indicating the ratio of these contributions that we have. So the one for honey, where the diffusive flux is dominating, so remember then the alpha would be the mu, the kinematic viscosity, so then the denominator would be large, the Peclet number would be small. The other way around, we have air for aerodynamic applications, then the diffusive flux will be small and the convective flux will be dominating. Then we would have large Peclet number, but if we discuss this for the Navier-Stokes equation, or this linearized Navier-Stokes equation, we would not talk about Peclet number, we would talk about Reynolds number, of course. But they just say what L is, where L is a characteristic length scale. So there is a definition here of the number. For example, if we would talk about an airfoil, we could have the chord length of a wing as a characteristic length for that. If we have flow in a channel, we could have the or a pipe would have the diameter or the height of the channel. So it depends on the problem. But then again, it would be the Reynolds number. Because then we would have here the velocity, the length scale, and here we would have the kinematic viscosity. Okay. Yes, and if we would have a large Peclet number, then convective flux would be dominating. For example, if we would have a large Reynolds number, then the diffusive or the viscous flux would not play a big role. except for boundary layers and wakes. So then we could neglect that outside boundary layers and wakes. We could neglect the diffusive effects, the viscous effects, and then we would have the 2D linear convection equation. So then we can see. And the other way around, if we would have a problem dominated by diffusion, where hardly anything is moving, for example, then we could neglect the convection part, and we would have then the diffusion equation. So but with the convection-diffusion equation, you have both present. And that is what we have in reality. So this describes what we observe in reality. Just the remark that I just made regarding to the case where the Kepler number is much larger than 1, then one can be approximated by the 2D linear convection equation. That we have the UDT plus, now we use again the notation from equation 1. And likewise, if the Kepler number would be much smaller than 1, then we could neglect the convection, and then we would get 2D diffusion equation. So then you can see the different limits that we can describe by the convection diffusion equation. And let's see. Also, for a Kepler number much smaller than 1, the convection diffusion equation can be approximated by the 2D diffusion equation. If we have a heat problem, then it would be the 2D heat equation. So that would be then the UDT is equal to alpha d squared u dx squared d squared u dy squared. And just what I already said for the linearized momentum equation, or if we talk about fluid problems, then we would then not consider the Kepler number, but we would have the Reynolds number. Kepler number would be Reynolds number. That is in our notation, it would be, if we had this problem for equation 5, then our convection velocity would be 0. We would take the modulus of that, multiply by the characteristic length scale, and divide by the kinematic viscosity. So that would then play the role that we have here with the Kepler number. What type do these equations have? We have now on the board just the limits. If we start with the limits, which type does this equation have? We have a time derivative and we have first space derivatives. That is hyperbolic. So that is an example of a hyperbolic PDE. So there we have just a transport, translation, and the quantity u is translated with the velocity vector c. c1 in x, c2 in y direction. The diffusion or heat equation, we have a time derivative, we have second derivatives. That is a parabolic problem. So we have there a diffusion process where sharp discontinuities get smoothed. If we have amplitudes, the amplitudes diminish. So that is. And what about the convection-diffusion equation? Which type is that? We have a time derivative, we have first derivatives, and we have second derivatives. It is decided by that we have a time derivative. It indicates that we have either hyperbolic or parabolic PDE, but it is decided by the highest space derivative, second derivative. So it has then the same character as the 2D diffusion equation. So the 2D convection diffusion equation is parabolic. Time derivative is there, and we have second space derivatives. Okay, so then we have the mathematical classification. Let's look at an example just in one dimension. This is the example. It is the same example that we had already before when we discussed the linear advection equation. So now it is both with advection and with diffusion. It is just in 1D to illustrate things. So you see here we have discontinuity. Here we have 0, but between x 0.2 and 0.4 we have 1. So, and it is now, this is a numerical solution, but it is compared with the solution, with the exact solution of the linear advection equation. So you see what is happening. So this is the exact solution of the linear advection equation. The diffusion has the effect that this discontinuity is smoothed. You see it here, and the largest value is diminishing. So if we would continue with that for quite a while, then this maximum would go down to 0. But you see that this smoothed profile is transported with the same velocity as in the linear advection equation. Here in this example the velocity is 1, and we had just done here a transport for a short time of 4. So that is the effect. Yes?
Jag har forskjell på den ligningen här och man bara brukte advection effect was on numerical diffusion? Or
That's right.
No.
That's right. Therefore, it is. So the point is, or the remark is, if we had computed that, for example, with the upwind scheme, we would have numerical diffusion, and we would have gotten something similar. But that is then a numerical error. Here, we want to simulate a physical effect. So if we have a physical diffusion, then it should be like that. But we should be sure that this is physical and not numerical. So therefore, that we'll discuss after the break how to discretize that, and also to estimate the error that we make when we do the discretization. That is actually the problem that we face when we do the discretization, that we will have some numerical diffusion present, but this should be as low as possible in order not to spoil the physical diffusion. We want to have the physical diffusion, and depending on that, the amplitude will diminish. What we have seen before, when we discussed the linear advection equation, that was numerical diffusion. It was nothing physical, just a numerical effect. But here we want to estimate the physical diffusion. So therefore we must be sure that what we are computing is physical diffusion and not numerical diffusion. So if you vary now the alpha, the diffusion coefficient in the convection diffusion equation, so you reduce that, then it will be more and more like the linear advection equation. In that case, the exact solution would be then that this would be more steep, and this minimum or this maximum would not have decreased that much. So if alpha would be 0, then we should get the exact solution for the linear advection equation. If we had just the diffusion equation, then we would have no movement, as we have here, but we would stay then here in this region, 0.2 and 0.4, and we would have a diffusion of this discontinuity over time. And in the end, it would go to 0. So the point with convection diffusion is that you have both physical mechanisms present: advection, transport, and diffusion, a smoothing effect. Okay, we stop here and take 30 minutes break.